Great. The recording is now in progress, so we'll start to talk about the material today. So today we're going to talk about cardinalities of sets. And cardinality relies on functions, relies very heavily on the material we covered last lecture. And I also think that this material is probably the hardest material in 300 other than the last lecture. Like I guess what I'm trying to say is it's the hardest material you're going to see so far. There was like a question in your homework that we thought was too hard, so we had to comment it out. You can still see the question in the overleaf document if you choose to look at it, but it is very difficult. It's a nice fact, but it's difficult how we ask you to do it. Okay, so let's go back to the basic. What exactly is cardinality? Well, recall from I think lecture 2, right? That the cardinality of a set is the number of elements that it has, or it's basically how big a set is, right? It tells you the size of a set, right? And for finite set, it basically tells you the number of elements it has. But how do we extend the notion of cardinality to infinite sets, right? So that means we actually need to formalize our notion of what a size of set is. A size of a set is. So here's our definition. We say that the cardinality of a set is less than the cardinality of another set, right? The size of A is less than or equal to the size of B when there is an injection from A to B, and we can flip the equality when there is a surjection from A to B. It's also a fact, right, that I think we're going to do next lecture, that A is less than, this is true if and only if, right, this is true. Right. It's also a fact that if this is true and what is B, right? So A implies that these are equal, right? So the intuitive inequalities kind of the intuitively these should make sense, right? These behave like kind of inequalities should, but we will get to this in the next lecture, okay? Mainly because we didn't actually write it down in this one, okay? But these are also facts, but these are, I don't think, too necessary to know. These two facts might be outside of the scope of 300. For example, I only saw that when I was taking the real analysis class, the 411 class, not even in 311. Okay. Also, I should note that some authors instead of A use card A for cardinality. So if you see this in other texts or other literature, then it's the same thing as cardinality. Okay. And we say that two sets are equinumerous, right? Or which means that they have the same cardinality, right? If there exists a bijection between them. Okay. Are there any questions? I hear chat. Is this why the title is Card Tricks? Don't ask me. I didn't write the title, but I think it's because cardinality.
Probably.
I didn't write the title for this lecture, so you can ask Adam. Yeah, I think that's why the last two lectures were titled relatively innocuous title, which I guess it has to do with relations. I don't know. But what is the intuition? Like my math, there is like this old-fashioned like analogy or something like that I heard when I was in 300, which I don't know how I feel about. But like the idea is that if you're in like a ball or like some dance thing, I don't know. I haven't been to dances or proms. And you have like a bunch of guys and a bunch of girls, right? Oh, you want to pair them up to dance, right? So and you would only kind of know how to do that if you can pair them up, right? Pair each of them up. And if there's one left over, then they don't have. If there's one guy left over or like one girl left over, then you don't have the same size. It's a very old-fashioned analogy. Do people still dance? I don't
Why don't you answer that question yourself?
know. Um, so like, I think there's probably better examples. Maybe like goats and sheep. I don't know. You can pair goats to like wolves or something to feed them. I don't really have a good better analogy. But that's kind of the basic intuition, if that makes any sense. Okay. Right. So before we even look at n to z, I think this is not the easiest example to look at. We're going to construct a bijection, right, from the natural numbers, right, to the even natural numbers, or right. So intuitively, right, this is right. I think this is like the first example. So intuitively, so we have the set of natural numbers. Someone wants to join. It's oh, allocating a bunch of COVID tests to people. That's a very nice example. Thank you. So if you have a bunch of COVID tests, right, and you want to allocate these COVID tests to people, right, you want to construct some kind of bijective mapping between COVID tests and people, right? And if you have COVID tests left over, like apparently in Florida, they had like 1 million tests stockpiled, and that were just gone bad. Then there's more tests than people, I guess. I don't know. So you can't construct a bijection that way, right? Right. So while Adam is here, let's ask him, why is the title of this lecture Card Tricks?
Cardinality.
Okay, so it is as you suspect.
It's confirmed.
Okay, it is as we suspected. Let's move on. So let's look at
wait, can I tack on something? It's
Is
like
there-
a fun
on.
historical tidbit for like.
Go on.
Okay, so basically like we didn't have numbers at some point in time, and so farmers would be like, how do I know that I have the same number of sheep on both sides of my fence? So they would go and line up the sheep alongside. Okay, that's it. Sorry. They would construct the bijection. Okay.
I actually talked about before you joined. I was talked about like feeding goats to wolves.
Okay.
And then the other analogy was like in a ballroom dance, pairing up the guys and the girls or together or something. That was the analogy that I heard when I took 311. That's 300, the ballroom analogy. But I was like, that's like a very old-fashioned one. Do people still have ballroom dances? Okay, so we're gonna look at the simpler example, right? This is not the most trivial example, I think, to think about. So what? So the natural numbers, right? There's a lot of them. And the even natural numbers, well, there's like every natural number. We showed that every natural number is odd or even, right? And furthermore, right, half of the natural numbers are odd, right? And half of the natural numbers are even, right? So I guess intuitively it should make sense that there are less even natural numbers or fewer than the natural numbers, right? But as it turns out, right, these two sets, right, despite this being like the half of natural numbers, right, these two sets are equinumerous. So they have the same size, which might be kind of unintuitive. Right, and in the bijection, right, is the obvious one. Send n, map n to 2n, right? And we need to show that this is a bijection. Well, every even natural number can be formed can be written as 2n, right? So you can divide by 2 and find your pre-image that way. And if you have the two even numbers there that are the same, well, they have to have come from the same pre-image, right? So you can those two that shows that this mapping is both injective and surjective, and hence these mappings are equinumerous. Okay. Another the same way you can, well, actually, never mind. You would need to actually prove that, but you can construct a bijection, right, from the natural numbers to the prime numbers. Basically by listing out the prime numbers, but you would need an extra argument to show that the prime numbers are not finite. And we haven't actually proven that yet, but it's not the most difficult proof either. All right, are there any questions so far before we move on? No, we don't see any questions. So we're going to look at our first theorem of the day. There is a bijection from the natural numbers to the integers, and it's like the same idea, right? The integers, right? There's the positive natural numbers and the negative integers and 0, right? So like the natural numbers are like half of the integers, kind of. But as it turns out, they are equinumerous. And by the way, how do the one way we can show that that a set is equinumerous to the natural numbers is to show that you can just pair them up. And from our earlier example, we can pair the natural numbers, right? 1, 2, 3, 4, 5. We match them up with 2n, right? So we match them up to 2, 4, 6, 8, 10, right? So what is the heuristic that we're going to employ here? Well, we're going to kind of weave our way across, if that makes any sense. So if you have the number line, right, something like this, there's 0, 1, 2, 3, minus 1, minus 2, minus 3. We want to enumerate these numbers somehow, and the idea will be to start from 0, go to 1, go to minus 1, go to 2, go to minus 2, and kind of go in this spirally kind of way. And eventually the idea will be that we're going to hit them all. Okay, but that's not actually a proof, right? Or actually, you can just say we can list them out like this: 0, 1, minus 1, 2, minus 2, etc. But that's not really. But what we just wrote down here isn't really a proof. It's just like a heuristic, right? So let's actually write down the proof. So we need to so when we want to show that these two sets are equinumerous, then we need to show that there is a bijection. And notice how that is an existentially quantified statement, right? That means we need to panic because this is going to be hard. Right. So we need to construct a bijection, and the idea is going to be this one. Okay. This is going to be the bijection. We're going to have to define it piecewise. Okay. F of n is defined as n over 2 if n is even, right? And minus n minus 1 over 2 if n is odd, right? So if n is odd, we're going to send it to the negative integers. And if it is even, we're going to send it to 0 and the natural numbers. Okay. Right, and that's the comment over here. F of n is less than 0 if and only if n is odd, right? Even naturals are mapped to positive numbers. Did I screw up? Oh, wait, the natural number doesn't include 0. My bad, I'm sorry. In our world, n is not 0. So the odd numbers are mapped to 0. Sorry, this is not the map that I usually think of. Yes, the odd naturals are mapped to the non-positive numbers. I'm sorry if there was confusion. Okay, so let's show injectivity. If you have a, b, and n such that f of a is equal to f of b, right? If they're both positive, well, then they must both be even, right? because of this, well, then a over 2 is equal to f of a equals f of b equals b over 2. Well, that means a equals b. Otherwise, if they're non-positive, then they must both be odd. Then you can still set up this equality, and if you or rearrange those two expressions, you get a equals b. Okay. Right now for surjectivity, if a is a positive integer, then you can then twice that number will map to that integer, and if it is non-positive, then you can think about the -2 times a plus 1 will map to a. And it's not hard to verify this. You just plug in this number, and then just verify that it comes out to a. Okay, and that shows that this is bijective. But again, right? You notice here, I'm going to emphasize again, this is an existentially quantified statement, so you have to come up with this thing. And for surjectivity, you have to come up with this. You have to come up with these two with these things that map to your element, right? So it's becoming a little hard. It might not be the easiest thing to come up with these two examples. Okay. Are there any questions? Oh, Adam is coding. Goodbye. Are there any other questions? I don't think there are any questions, right? Great. So let's look at our next example, right? Well, we showed that the natural numbers has the same size as the integers, right? So what's the next step up? The next step up is, of course, the rational numbers. So if the question is there a way, right? Is there a bijection between the naturals and the rationals, right? And that question ultimately boils down to, is there a way to list out the rational numbers in a systematic way such that every rational number appears once, and every rational number actually appears? And the answer, it turns out, is yes. And this might be again very non-intuitive, because, and why is this? The rational numbers are, we say they're dense in the real numbers. That means between any two real numbers, right, we can always find the rational number in between. So there's like a lot of rational numbers, but it turns out, right, that it's still not that many as there's still not as many rational numbers. There's still as many rational numbers as the natural numbers, right? So like which is very non-intuitive, right? So between 0 and 1, there's no natural numbers, and there's like a crap ton of rational numbers in here, but we can still list them out. We can pair them with the natural numbers. Okay. All right, does this make sense? Well, probably shouldn't, because we didn't actually present the proof yet. And how do you do this, right? We're not gonna present the proof yet, so we're just gonna present like the sketch of it. So the idea is to use a 2D grid. Okay, so we're going to oh, he's writing from top left. Sure. So I'm gonna write we're looking at Q plus, right? Yeah, positive. So I'm gonna write, right? So there's so 1 in row I in column J. So I'm gonna write 1 over 1 here, 1 over 2 here, 1 over 3, 1 over 4, and dot dot dot. And now I'm gonna write 2 over 1, 2 over 2, 2 over 3, 2 over 4, 3 over 1, 3 over 2, 3 over 3, 3 over 4. And the idea is we're going to go this way, right? And then this way, and this way, etc. And then this is going to give us, right, a listing of the rational numbers: 1 over 1, 2 over 1, 1 over 2, 3 over 1, 3 over 2, 3 over 3, etc. Now, all the while, we're going to delete the duplicates. So where are the duplicates? 1, 2, 1 have 3, 3 have, this is a duplicate, right? Did I miss one? No, this is, oh, that's a 2. That's not a 3, that should be a 2. This is a 2, right? Yeah, that should be a 2. Something smells like 1 over 1, 2 over 1, 1 over 2, 3, 1, 2 over 2. That should be a 1 over 3. What am I doing? 1 over 3, so we wouldn't delete this, right? But we would delete this. Okay. But does this make sense? Does this make sense to everyone? Great. So now all we need to do is formalize this notion a little bit. Okay. So so here's our definitions. We say a finite sequence on an arbitrary set, right? A is a function going from the subset of naturals from 1 through n, right? To A for some n in the natural numbers and 0. We're going to this thing we're going to write to be the empty set. We say that A is a finite sequence of length n, right? Where AI is the A sub I is equal to f of I. An infinite sequence, and we say an infinite sequence, right? As I think we said this before, is a function from n to an arbitrary set A, and usually, excuse me, when you say sequence, usually when you say sequence, you usually mean an infinite sequence. But for the purposes of this lecture, we're going to differentiate between a finite sequence and an infinite sequence. Okay, and sequence, no one actually thinks of sequence as like a functions, but they are, because it maps n to an, right? Right. Their next definition: if you have two finite sequences on a set A. Oh, I don't like this notation. All right, I don't like this notation. I'm gonna write A sub n like this, or k, let's say, from k equals 1 through n, or if it's infinite, we're gonna write ak k equals 1 through infinity. Okay, so if these two are finite sequences with n and m elements respectively, then we say their composition is a finite sequence with n plus m elements and is defined by this function. Basically, what is the idea? We're just going to concatenate these two finite sequences together. Okay, that's not too hard, right? I'm going to choose to believe that is a typo. Did I make a typo somewhere? Is there a typo somewhere? Okay, I don't know what that is saying. But yeah, I don't know what you're saying exactly. Oh, notation. Yes. Sure. So usually, and the reason why I don't like this notation too much is like when you use curly braces, usually it means that these things are unordered, while in sequences order matters. So yes, and parentheses, just using parentheses usually means that order does matter, right? So that's why I prefer that notation. But some books just use this, right, and from 1 to infinity, which just shows that it's an indexed collection, which is fine. But if you don't put an index, then it's just, I don't like it. But that doesn't matter. We'll go on with the actual material. This lemma is composing an infinite sequence of finite sequences yields an infinite sequence, and that should, intuitively that should make sense. If I have like right, if I have A, B, right, and this is like this sequence of length 2, 3, length 2, 4, etc. And if I compose them, right, if I compose them, and there's infinitely many of them, I'm going to get an infinite sequence. Okay. So here's the proof. Let A be an arbitrary set, and let B be this set of finite sequences on A, right? And let B be an infinite sequence on B, and let L be a sequence of lengths of sequences in B. Okay, now let C be the composition of all sequences in B. Okay. To visualize, see, the first L1 elements are going to be the sequence B1, right? So like this. So we're going to put this first sequence first, and then the second sequence, and L2 sequence, and so forth, right? We're going to write S be a function, S for sequence, going from 0 union n to 0 union n, where S of 0 is equal to 0, and S of I is equal to S of I minus 1 plus Li. And this is basically going to be like, this is basically going to be the, this is going to be the indices of our new composed sequence. Okay. S is a prefix sum of the lengths of sequences in B. Okay, that means we can define, right? Now we can actually define the new composed sequence explicitly, right? It's going to be like this, where in our notation it's over like this. Right, once I exceeds the new Sj, we're going to switch to the next sequence and find the correct index to use in that sequence. And C is infinite because it had a finite number of elements, right? And then there would be no elements. It would be sub n plus 1 onwards. This, I don't know, I feel like a lot of this is formalism, right? But you should just think about the intuitive idea, right? And all this notation is just formalizing that notion in a lot of the notation. This is just one of those proofs where the notation is hard to get through. Notation is harder to understand than the intuition. If you get the intuition, then then you're basically fine. But it might not be a bad idea to return to the proof of this lemma after the lecture, because in fact, if you smell something fishy with this lemma, then you might be onto something. Okay. All right, but with that having been said, are there any questions? I don't think there are questions, right? Right. Oh, makes sense. Great. Right, your homework will be to find out what the fishy part about this lemma in the proof is. Okay, something's not quite right here, but that is going to be up to you. All right, but the next thing is that we're going to construct a bijection from n to q, and the idea, right? What is the idea, right? This is each of the diagonals here is going to be a finite sequence, right? Because these lengths are of the first diagonal has length 1, the second diagonal has length 2, the third diagonal has length 3, etc. And the idea will be that we're going to be composing these sequences together. Okay, so let B be a sequence of sequences of positive rational numbers, and define Bi, right, B to be a sequence of positive rational numbers whose numerators and denominators sum to I, right, such that they have not appeared in any Bj for j is less than 1. So what this is saying, right, this Bi is a sequence of diagonals such that, right, after we have thrown out all the duplicate elements so far. Okay, and now we're going to compose these sequences together, which is going to be an infinite sequence. We're going to show that this is a bijection. Okay, so suppose we have two elements that are the same, then these two rational numbers are then they're we can write them in lowest rational number in lowest terms. But the sum of the numerator and denominator is the minimal when the rational is in lowest terms, right? Because otherwise, if it's not in lowest terms, because if it's not minimal, then you can divide both the numerator and denominator. That's basically what lowest term means, right? Then P over Q must appear in that sequence P plus Q, right? And there is no smaller index K such that BK could contain P over Q. So these two rational numbers appear in the same sequence, but this sequence should not contain any duplicate elements, right? And it doesn't appear, right, in any elements in any other sequence in the future because we have constructed it such that we're going to throw out any duplicates before. So therefore, these two must have come from the same natural number. Okay, and now surjectivity is even easier because if P over Q is a rational number and positive rational number in lowest terms, right? Well, then a rational number in lowest term must appear in B sub P plus Q, so it must appear somewhere between these two indices. Okay. All right, so that means so that means we have constructed a bijection between the natural numbers and the positive rational numbers. So that means they have the same cardinality. Okay. All right. So their next definition, right? Where you say that a set is countable if it is either finite or equinumerous with the natural numbers. We just showed that. What did we just show? We just showed that of course, the natural numbers is itself countable, and we also showed that the integers are countable, and now we just showed that the positive rationals are countable. And if we say that a set is infinite and countable, then we say that the set is countably infinite. Okay, and if a set is not countable, then we say it is uncountable. Okay, one other what is it? One other piece of vocabulary is that some books or some texts, instead of using the word countable, use the word denumerable. Okay. Because denumerable just means that you can enumerate the elements, which just means that you can construct a bijection between the natural numbers and the elements of the set. Okay. Are there any other questions about these two definitions? Okay. Now, so we just saw some examples. Excuse me. We just saw two examples, or I guess three, right? Of sets that are countably infinite, right? We looked at the even numbers, right? Even natural numbers are countably infinite. We said the integers are countably infinite, and the rationals are countably infinite, right? So the obvious question, right, is now, okay, is there a set that is uncountable, right? And it turns out the answer is yes, right? And our theorem says that we're going to say that R is uncountable. Is that R is, the real numbers is not countable. Okay, and for the sake of simplicity, we're going to, instead of R, we're going to look at 0, 1. And it turns out, right, there is a bijection between 0, 1 and R. Bonus points if you can. Well, can anyone think of a bijection between 0, 1 and R right now? I think we still have some time left over. I think this is the second to last thing we're gonna do. Yeah, we're almost done. So can anyone think of a bijection between 0, 1, and r? You could probably manipulate tangent. Yep, that's exactly what I'm thinking of. My favorite bijection between 0, 1, and r, I think, is tangent of pi times x minus pi over 2 or something. I think this does the trick. This is the does this do the trick? I'm not entirely sure, but I think this, I'm pretty sure this works. But yeah, you can manipulate tangent of x or in some general rational with vertical asymptotes. 1 over x minus 0.5. I don't think that works actually. That doesn't seem good. You need, because that only has one asymptote. Oh, or you mean, does that work? I don't think that works. Because you need to yeah, no, I don't think that particularly works. But tangent is going to, I think there's like one with something around, it's something like x over like 1 over x squared, 1 minus x squared or something. It's something like that. I think that that works. What is it? Yeah. One, yeah, I think this is the one, or is it pi x? I always forget. Oh. Yeah. My apologies. It's actually not this. The parentheses is in the wrong place. It's this. This is going to do the trick. Yeah, 1 over x times x minus 1. I think that might work, but I think, hold on, x times x minus 1. No, that doesn't quite work, I think. Yeah, something, well, but that's okay, but because this is fine. This is going to do the work, and I think this is like the most common example anyway. All right, but this produces a bijection from r is from 0, 1 to r. Okay. And in fact, right, it's true that in fact, this was actually going to be one of your homework problems, but it's true that you can produce a bijection from 0 to 1 to r, and similarly 0, 1, this is a parentheses, to r, right? You can produce bijections like this. Okay, can you think of anything? Make a cotangent at that point. Do you have any ideas about how you can produce bijections from the closed and bounded interval 0, 1 to r, or the half open, half closed interval 0, 1 to r? Any ideas? Yeah, you're going to need to make it piecewise. In fact, any continuous attempt is going to fail. You're well, I don't know about this one. Is there a continuous one? There is there a continuous one? I don't think there might be. I'm not sure about this one. I don't think there will exist one, but any continuous attempt is going to fail here. And why? Well, you all took 291, yes? No, if it has asymptotes in the if it has asymptotes in the middle, then that's not the whole domain, right? Then it's not bijective. You all took You all took 291, right? You all should remember that continuous functions preserve compact sets, and 0, 1 is compact, while R is not compact in the usual topology, and therefore any continuous attempt to produce a bijection is bound for failure. Okay, but 0, 1, of course, works. All right, but maybe that's a little too much for now, maybe. So let's move on to the actual proof. Okay, so we're going to just work with the open interval 0, 1, and n. And there's a natural injection. Well, it's not very natural. And, well, you don't even need to go from 2, 0, 1. You can just go, there's a natural injection from n to r, and that's just map n to n, which shows that n is, oh, sure. N is less than or equal to r. Okay? I don't think you need to go this far. Or you can just map each n to 1 over n, I think, or n plus 1, I guess. That should work. I don't know why Adam goes through the work of both of like negating it and multiplying it by and like subtracting one. What is it? Taking the 1 minus of that. This should just work. Anyway, but you can just take an injection. It's possible, right? And the next thing is going to be the famous Cantor's diagonal proof. This is actually a very sketchy proof. There's a few details that that are left out. So we got some time, so let's actually think about some of the details. Okay. Now, if you wrote something like this, you would probably well, get some points taken off for style, actually. So your first step should be towards a contradiction, right? Suppose, right, there is a bijection from f from n to r, which says towards the contradiction. Suppose there is a what do I want to say? Suppose suppose they are equinumerous. Yes. Okay. So what does that mean? If there is a bijection, right, then 1 maps to something, and in fact we're going to, and I'm being stupid, so 0, 1 and not r, right? So 1 is going to map to some r1, 2 is going to map to some r2, 3 is going to map to some r3, and so on, right? Okay. Now, these numbers, right, all have decimal expansions. We're going to take that for granted, right? So I'm going to write them as 0.r11, r12, r13, etc. All right, and 0.r21, r22, r23, etc. And 0.r31, r32, r33, etc. Okay, so we're going to take the decimal expansion of each number in this sequence over here in this. Okay. So can anyone tell me, Tyson Bunkers? I don't know what you guys are talking about. Can anyone tell me what the problem with this is right now? There's a slight problem that you need to kind of work out. The kind of wrinkle in the proof.
Am I allowed to say anything?
No.
Okay.
Well, maybe you can take some time to think about how can we make these decimal expansions. Well, just every real number has a decimal expansion, right? But what's the problem with that? Every real number has a decimal expansion, right? I mean, we can just take that for granted. Every real number has a decimal expansion, right? Like 1/3 is 0.3333, you know? But what's the problem here? You're close. How can we you might want to think about how can we make these decimal expansions? There's something in there. There's a wrinkle that you need to iron out. Yes, what is everyone's favorite math gotcha in high school? Sure. This wrinkle isn't actually talked about in I don't think it's in the proof that Adam wrote either. Yeah. That's why it's a very sketchy proof. In all the proofs of Cantor's diagonals, this is the one wrinkle that you need to like kind of work out. And this type of wrinkle was actually what was difficult about the problem that we were going to give you. It's very annoying. Maybe I'll give you like 2 more minutes to think about it. Think about, do we have to go through infinite elements? No, that's not quite the problem here. What about like 1/4? What's the decimal expansion of 1/4? Or 1/2? Can anyone tell me? Or is that right? Yes, the decimal expansion is 0.250000, etc. But on the other hand, right, I can write 1/4 is equal to 0.2499999. Repeating, right? So it turns out, right, there are some numbers that have two different decimal expansions, right? And that's the problem. How do we make the choice? Because 1/4, is equal to 0.25, and then zeros, a lot of zeros, or equal to 0.24999, right? These numbers have two different decimal expansions, right? Remember in high school, you're just like, haha, 0.9 repeating is 1, right? This representation is actually a shorthand for, a geometric series, right? But like these, all the proofs that you saw in high school has some things that you're sweeping under the rug, and it doesn't actually formalize some of the notions that there's some notions that you probably need to formalize if you want to think about this properly. You're going to do that in analysis, so not going to delve into there too much, but that's the problem. Some numbers have like two decimal expansions, right? So how do you choose one? So in the beginning, you're just going to say, okay, for every number, right, that have two decimal expansions, right, you're just going to choose one representation, right? You can choose this or you can choose this. It doesn't matter. But all you need to say is that you need to say that you're going to stick to one representation throughout the entire proof. Okay? Does that make sense? Okay, so that means we have a consistent way to write down every number, right, between 0 and 1 in a consistent way in using decimal expansions. Great. Now, right, consider the number. Let's call it r star given by let's see 0 point r let's say s1, s2, s3 dot dot dot, where, right, s1 is given by let's say how do I don't remember what the actual thing. Oh, right. Let's say what's your favorite number, the digit between 0 and 9 or 1 and 9? Seven, sure. 7. Why is this like this? 7, right? If R11 or R, let's say JJ, J is not 7, and let's say 6 if RJJ equals 7. All right, something like this. Okay, well, I claim that R star does not appear in any of these. Why? Well, if you look at the first digit, it must differ from the first one because, right, if R11 is 7, well, this one is 6. And if it's not 7, then it's 7. So it has to differ from in the first digit from this first number over here. And in the second number, well, it has to differ in the second digit, right, by a similar logic, right? And it has to differ in the third digit also. So this number that we cooked up differs from every number that we listed over here in the jth digit. So that means this number doesn't appear in this list. That means this isn't surjective, and that's a contradiction. Okay? So, does that make sense? Is everyone okay with how I cooked up R star and how I cooked up SJ and how I cooked up and where the contradiction came from? Because this diagonalization argument comes up in different contexts also. For example, you can I think this diagonalization argument is what is it? I think it's used as a in the proof of the solution to the halting problem, in a solution to the halting problem. So it comes up in a variety of places. Okay, if you if you like theoretical computer science or whatever. Okay. No questions. Great. Okay, so what did we just show? We showed that the real numbers are strict. The cardinality of the real numbers is strictly greater than the natural numbers, right? We say that the cardinality of the real numbers is C, right? For a continuum, we say that this is the cardinality of the continuum, right? And you might be asking yourself, okay, so is there any cardinality between the cardinality of the continuum and the cardinality of the natural numbers? Well, it turns out, right, that this is the cardinality of this was a continuum hypothesis. Does there exist a set C such that its cardinality is between that of the natural numbers and that of the real numbers, right? And we write the cardinality of the continuum with the fractor C, okay? And it turns out, right, that the continuum hypothesis is independent of ZFC, right? So it can either be true or false, right? And it can be true or false, right? And I don't remember when it was proven. But
Professor Ko, what is ZFC?
we looked at, please revisit revisit chapter or lecture 2. We talk about ZFC. We talk about ZFC in lecture 2. Okay. But it turns out that this is
Proved by Paul Cohen in like the 60s, I think.
yeah, it was a huge deal when it was proven. Like I think the dude got a Fields Medal as a result of proving this type of thing. And so it can either be true or false, and the axioms of set theory will be consistent either way, and we say it's independent of the logical system. Any questions so far?
Paul Cohen was also from New Jersey. Just wanted to say that. So New Jersey pride. Yeah, he proved it in 1963.
All right. Before all of us were born. No questions so far? Great. All right. So the last thing we're going to do before ending today is we're going to do Cantor's theorem, which I think we promised that we would do in lecture 2, right? Which says, right, for any set X, right, the cardinality of that set is strictly less than the cardinality of its power set. Okay? Or we can just say there is no injection from the power set, right, to its or there is no surjection from a set to its power set. All right, and there is a trivial injection from x to the power set of x, right? So for each x in the set, right, you can just map it to the singleton containing the set, right? And this is injective, right? I don't think there's any, there's probably no like objection to the fact that this is injective. So we know that this is true. Now, right, towards a contradiction, suppose there is a surjection from f from x to the power set of x, right? And now consider the set, right? Consider the set x in consider the set A. I'm gonna write this down. A defined as x in x such that x is not f of x, right? F, remember, right? F goes from x to the power set of x, right? So this x is a set containing the elements that is not in f of x. Okay. Well, f, right? But f is on 2, and a is in the power set of x because it's a subset of x, right? So there must exist an a in x, right? There must exist an a in x such that, right, f of a is equal to a. Okay, and now the question is a in f of a, right? Well, right, if a is in f of a, right, then, right, well then, you know, then by the description of a, right, which is equal to a, well, a is not in f of a, right? But if a is not in f of a, right, well then by the definition of a must be in f of a, right? In either case, we get a contradiction, right? So both of these possibilities are impossible, right? The contradiction has arrived, and the proof of Cantor's theorem is complete. Is everyone okay with this construction and where the contradiction arose
You
from?
really wanted to say that, didn't you?
I really wanted to say that. Is everyone okay with this? Okay. Okay. And as one more comment, right? This sentence is from Helmholtz's Naive Set Theory, which is a wonderfully written book. You should definitely read if you have the chance. Right. Are there no other questions or objections, for that matter? Is this set valid under ZFC? I think it is. I'm pretty sure it is. Oh, that's like the set of sets that does not contain. Does the set of what is it?
Yeah,
Is
it's
it
Russell's paradox.
paradox? The set of all sets contain itself, or is it something like that?
The sets of all sets which do not contain themselves.
Oh, something like that.
Like the barber analogy. I don't know if you guys talked about the barber or not.
But this is what do I want to say? I'm pretty sure this. I think this proof is.
I don't think there's
valid.
anything in here, right? It's just
No, I
the set of everything that's not in the image, right?
Yeah.
So
This set should be fine, I think, in ZFC. Well, first of all, if it weren't fine, then why would this is the standard proof, right? So if it's not fine, there's no reason why it would be the standard proof. Is that
yes,
like kind of this
proof
meta
by
argument,
appeal to authority.
right? Right.
If this proof were wrong, it would not have been taught to me. So therefore,
Yes.
it's correct.
Precisely. That makes sense. Are there any other questions? With the continuum hypothesis being independent of ZFC, what about it? Please don't ask me to produce a proof of that. Does that mean ZFC, no set in ZFC can be constructed to have cardinality between Z and R? That means like the axioms of ZFC does not imply, right?
It means that it's neither true or false, right? Or
right.
that
So you can have a set, right, of cardinality between Z and R, and basically that'll have no contradiction between that will produce no contradiction with the axioms of ZFC, and rejecting the idea of such a set will still not produce a contradiction with ZFC. At the same time, ZFC will not imply the existence of such a set, and ZFC does not imply the non-existence of such a set. Does that make sense?
So in essence, you can just shrug your shoulders and assume whatever you want. And there are valid constructions of this is entirely like set theorist insanity. So I don't know a ton about it, but I do know that some like set theorists work in models where there are like at least like 3 or 4 different kinds of infinities of size in between N and R. And there's some that just reject the continuum hypothesis. Like there's you can go either way. It's independent from ZFC in that respect.
If you're interested, then you might be interested in taking the set theory course, which is offered every fall. Okay, it's like 361 or something.
We'll see if Simon Thomas teaches it again.
Well, I don't know if he is. I don't know if he's on sabbatical next semester.
He's
on sabbatical this semester. Is his sabbatical like a year long or not?
I don't know. Maybe it is. I'm assuming.
When was his last sabbatical?
I have no earthly idea.
Because like if a professor has year-long sabbaticals, apparently they have it every 7 years. So but if there are no more questions or objections, then I will end the recording. If there are questions, then speak now or type now.
I think someone has a question.
Who has a question?
I don't know. It sounds like you hear it in the background.
All right, I'm gonna stop the recording.